Hi all, thank you for joining. My name is Alex, and my only credentials for giving this talk today is none other than having spent the best part of the past 15 years arguing with distributed systems, most of the time being on the losing side of those arguments. So my motivation when I submitted this talk was to help others, hopefully some of you, to be on the winning side of those arguments more times than I've been. So how will I try to do this? First, I'll introduce you to our case study, and then we'll see the decision-making and thought process we went through as we split a monolith into microservices. Then we'll see the hell that this decision unleashed, and in the form of distributed transactions. So we'll see how we tackled those, and then we'll close with what is the best or the best bang for your buck in terms of gaining resilience and stability in your system, which is proper timeout and retry policies. So let's get started. The system we'll walk around today is a player account management platform. For those unacquainted with the term, it's a pretty standard system in the online iGaming world. It is where our users register, onboard, and verify themselves. Successful completion of this process gives them access to an online wallet, which they can top up and then use it to play our games, all under responsible gaming supervision. So when we initially launched our PAM at OPAP, these were more or less the components it was composed of. And today we'll focus most on the wallet. Two reasons. It's the one I find most technically challenging, and it's the one I've been involved in the most. So it was essentially a monolith. And this was by design. It allowed a small team of engineers to iterate fast and deliver in time an enterprise-grade, production-ready wallet, and by extension, PAM. Of course, it being a monolith, it did pretty much everything under the sun. It was obviously responsible for keeping track of the user's account balance and their monetary transactions, but was also responsible for completing more complex flows, such as deposits, withdrawals, bets, and responsible gaming. A bit more on this. So whenever a specific function goes on in the system, it's responsible to keep specific metrics to keep track of those. So it doesn't allow our users to go beyond a specific threshold that they had set themselves. And this was also implemented within our wallet. Arguably, the two most important functions in a PAM are bets, which is pretty much the reason our users register with us, and deposit, essentially our online products only revenue stream. Now, there's some things in common and some things pretty different in those functions. Bets tend to come in much higher volume and usually require immediate feedback on whether the bet was accepted. Think about live betting, this sort of thing. And they tend to be more elastic in terms of traffic. So when we have big sporting events, or in our lottery world, when we have a big jackpot draw, we have a much bigger factor of traffic increased in bets compared to other functions. Deposits, on the other hand, we have noticed that our users are more tolerant when it comes to delays, most probably related with the fact that there's some sensitive data that they're entering and flows through our systems when they're doing it. Both are governed by responsible gaming rules. So we had a wallet, we had a PAM ready in production, but we had a lot of work to do if we were to catch up with our business competitors, which were some pretty big names in the market. So we have a huge backlog that kept getting bigger, and as a consequence of this, our team scaled up, which had the unfortunate side effect that we started spending more time resolving merge conflicts than actually implementing features. And we have some important features that we needed to deliver. On the product point of view, we needed to be able to offer our players alternative payment means to deposit with, but there was also the regulation stream. Now, even today, but more so a while ago, Greek online regulator tended to be much volatile. So if we wanted to keep our online licenses, and most of us did, we needed to be able to streamline those to production within a very short time. This was around the time when we considered that we might start making our services a bit more granular. In their perhaps a bit dry but definitely invaluable book on software architecture, Neil Ford and company define what they call granularity disintegrators, which is essentially a fancy way of saying reason to justify carving your services out. What they define is scope and function. Is my service doing too much? Code volatility. Does part of my code base change more often than the rest? Scalability. Do I have different scaling needs for only part of my functions? Fault tolerance. Are there specific services, functions that fail much more often than the rest with the danger of pulling everything down? Of course, security. Are there specific security considerations that apply only section of our application? And my favorite, extensibility. Does it make sense to split something out in expectance of some future implementation? Now, it took us a while to get there, but this is what we came up with. We grouped what was deposits and withdrawals, money in and out of a player's account, into what we named the payment service. We carved all the bets into a newly implemented betting service, and we moved all responsible gaming limits functionality in a newly baptized RG service. Now, from a domain-driven design point of view, these services made sense to us. We felt like these were pretty well-defined, bounded contexts that we could use to reason about with our business owners. But also when it came to the technical justification we saw earlier, there were some drivers that were also checked. Obviously, all three were part of this big monolith that was definitely doing too much, but there's also justification on a per-service basis. For example, our payment service had this stream of new payment means that we needed to add, so there was a lot of code changing there. And there was also the option for a user to perhaps store some payment information for future use. So we had the security aspect to take into account as well. Our betting service biggest justification was this elasticity in scaling it. And our RG service similarly had a lot of changes regulation-wise, but also extensibility. Now, you can see when we pitched to management our idea to go this way, we had to add extensibility as a justification for all services, but this is where it really made sense. Now, the thing is, up until around that day, responsible gaming limit was defined only in monetary terms, which is part of the reasons why it was also initially within what we saw in the wallet service. However, there were new regulations that were going to come out where it would define responsible gaming in other aspects as well, like time limits. How much time would a player allow themselves to spend on our website? So it made sense to prepare for what was coming and move it out separately. So this is what we came up with. The big wallet service gave birth to 3 new services, which for most flows, they were pretty, they could stand by themselves, they could complete them. However, there were other flows, important flows, that we needed to have those interact somehow. And this is where we reminisced the good old days of the monolith because we exposed ourselves to distributed transactions. Now, things we had like the ACID properties of a local transaction was now completely off the table. We'll spend the next part of this talk to see how we went about implementing them, and we'll analyze them in 2 axes. Communication. How do services communicate with each other? Is it synchronously with something like HTTP REST or gRPC? Or is it asynchronous? Do they communicate by using some sort of message broker? And we'll evaluate also the coordination axis. How does each service know when to do and what to do? Is there some sort of central orchestrator telling everyone what to do? Or is it more like choreography, where services react to events going on in the system, or perhaps to requests they receive? First, we'll see how it went with our synchronous flows, which is, I would assume, more our standard service-to-service call in a microservice architecture. I would assume around 80% of our code base works in some sort of this way. If we imagine the cap continuum, this tends to be on the consistency side of things, especially compared to what we'll see later. And they come in an orchestrated or choreography approach. Now, if we're to go through our betting flow in the monolithic approach, this was more or less what it looked like. We had a betting endpoint exposed by our wallet, and now within a single transaction, we would store this into the database, perform the RG metrics update and make sure the user was okay to proceed, and then we update the balance. We withdraw the cost of the bet slip from the user's account. Our initial approach to redesign this was to go with the synchronous choreography approach, where essentially we have chained requests from one service to the next. Now, the betting endpoint was now exposed by our betting service, which, when called, it would do its thing internally and then issue a synchronous HTTP request to our wallet. Now here, probably a leftover of the days where the responsible gaming limit check was within the wallet, it would be the wallet that would be checking against our RG service about to make sure that the RG metrics are updated and make sure they can proceed. If everything was successful, the user was getting the response that their bet was placed. So as an overview of this approach, in terms of coupling, essentially within this chain, each service is coupled to its neighboring one, which is, it's okay, I guess. Error handling and error propagation tends to be easier than what we'll see later. However, there's this issue where, exactly because we have chained requests, we might need to have some sort of data from the first node reach the last service. So it needs to go through everything in between. So this can lead to some sort of domain contamination or domain leak. It's ideal for relatively small flows when we implement them, and the more steps are added in our flow, it can grow and maintainable, which is what happened to us. And more specifically, responsible gaming betting-related checks started to become too specific within a betting context, so it didn't make any sense to keep it being performed by our wallet, so it needed to be moved outwards. Additionally, there was a new requirement where we had specific users being excluded from betting, so we needed to make sure that a user could place a bet before they proceeded. And we had some fancy new business features like email me my ticket, this sort of thing. So we went on and redesigned our redesign, and we went into what is the orchestration approach. Now, essentially what we have changed here is now the betting service acts as the orchestrator and knows which step to perform along the way. Now, in this approach, we have the first request to our access service to make sure that the access is allowed. It would then perform the request to the RG service to update the RG metrics. And if those are successful, it will call the wallet to withdraw the cost of the betting slip. Finally, a request to our communication service to notify the user if they had selected to with a bet slip. It was in this iteration that we most felt the lack of local transactions, of ACID properties. What happened? These two, the request to our RG service and the one to our wallet, were the two state-changing requests. So what happens if this one succeeds? It has its state changed, but this one gets rejected. The user has no balance. This is where the concept of compensating transactions comes in handy. Now, given a series of successful requests, if one gets rejected, what we need to start doing is going backwards. We can't roll back. There's no global transaction. We need to start going backwards and undoing the changes we did in the form of compensating requests. So if we are to see this in further detail, the flow, the access check passes, so does the RG limit update, but the user doesn't have enough balance. So what the orchestrator ought to do, starts going the flow backwards to undo what it successfully did. In this case, like I mentioned, the only state altering, the only mutating request was the one made to the RG service, so it performs an undo request to that. Had a request to our access service been a state altering as well, this would be the next step in our flow. So an overview of the orchestration approach, it allows each service to be much more less coupled and more granular. However, the orchestrator is pretty well coupled with all the downstream services. This is where it really makes sense to understand the help of compensating transactions. And like I mentioned earlier, as the more the complex a flow gets, the more sense it makes to have an orchestrator. Of course, it's much more maintainable as an approach because you get to have within the orchestrator, within perhaps even a single class, the whole flow implemented, which can be a double-edged sword because it can lead to having really, really smart orchestrators and downgrading the participating services to crowd operations. So we need to keep this into account. Of course, the orchestrator is essentially a state machine, so we need to have codified all the state transitions. And of course, it will fail, so we need to have some sort of mechanism that will be able to recover in case we fail in the middle of a flow. The other big flow that we were required to redesign was the deposits flow. Again, in our monolithic version, it was pretty simple. A deposit endpoint exposed by our wallet. The wallet would store the deposit in the database. Again, perform the RG calculations, make sure everything's in place. Optionally, the user could have selected to store that payment method for future use, and then add the deposited amount to the user's account. All under the warm bosom of a lovely ACID transaction. If we were to follow a similar approach with an orchestrated synchronous flow, again, it would look eerily similar with what we previously saw. An orchestrator issuing requests to downstream services. We have a small change here. Well, it would call itself to store the payment method, but it would be more or less the same. I mentioned, however, that essentially deposits are our online products only revenue stream. So when this is the case, it does make sense to keep an eye on your total availability. So had we gone with the synchronous approach, what we would have would be that the deposit function's total availability would be directly dependent to the uptime of those three downstream services, which, assuming a 99.9 for each, but mathematically we cannot have a total availability beyond the 99.9 threshold, which means we have at least of a total downtime of 26 hours within a year. Now, there are some cases, not many, but there will be some cases when it will make sense to try and squeeze some availability out of your architecture. And this is where sagas come in handy, which essentially is distributed transactions over asynchronous messaging. Again, if we imagine our cup continuum, these tend to err on the side of availability, and they come on a choreography and orchestrated approach. So what we essentially gain is to ditch the direct dependency to those services and make it indirect over this message broker. So essentially, our total uptime is now directly related to the message broker's uptime. So what we have done is we have gained 17 hours of uptime within the year, which I need to make it perfectly clear, in no way does it come for free. The first approach we attempted to implement the deposit flow was the choreography approach, which essentially there are events happening within the system. You listen to those events and you react to those. So it sounds amazing. And if you already have an event-driven architecture, it suits perfectly. But we didn't, so we thought this was a good opportunity to introduce event-driven into our infrastructure. So we codified the flow a bit like this. The payment service, when a deposit is created, the payment service would do its thing and then publish a deposit created event. Now, the first step in this saga would be the limit check. So we have the RG service that is hooked into this event and performs the required updates and checks. If it's failed, then an event is published. Maybe we can hook a communication service to listen to those events to let the user know. If it's successful, then we have the next step in our saga, which is the wallet performing the balance update. Again, this could be successful or unsuccessful. In the case it's unsuccessful, a balance rejected event is published, and we need to have our RG service hooked into this event to perform the compensating transaction, to move its state back. If it's successful, then we have our payment service hooked into the successful event, and more or less our flow completes. If we gather the events that we saw in the subscribing and publishing services, this is what we would gather, and we were actually in the whiteboard, gathering these, writing them down, when we were like, okay, wait a minute. This is what we were moving away from. This was 300 lines of code, 400 lines of code in a couple of Java classes, and what we were moving into was a huge leap for us. And I think in this approach, complexity would be my main criticism, if I may say so. You need to, sometimes it can be hard to maintain, to document, sometimes even to understand the full flow if you don't have it somehow documented in front of you. Definitely, the choreography Saga implementation suits well already existing event-driven architectures, but chances are, if you're already there, if you're already event-driven, you're most likely already using some sort of Saga implementation, but you might be just calling it differently. So definitely, it's worth keeping in mind that if you're going to proceed with this, make sure that you have the buy-in from the people who will be implementing this, supporting this, debugging this, before proceeding. Also, make sure that you have the proper processes in terms of documenting those flows and keeping track of them in order to make sure you don't end up in a big ball of event-driven mud. In our case, we thought it was just one leap too far for us and a flow too complex to go with the choreography approach. Not that the one we implemented was simple, but it was simpler to us at the time. We went the orchestrated approach. Now, here essentially what we see is the payment service acting as an orchestrator, and the endpoint that it provides is a deposit endpoint. It will do its thing internally, and when it's done, it will issue the first step of the Saga, which is a command for the RG limit sec to be performed. Now, as soon as this command is published successfully to the message broker, we return successfully. And this is exactly the point when we start gaining on availability. However, it's also exactly the point when we start losing on consistency until the successful or unsuccessful completion of the full Saga. So let's follow the flow through. The message broker will deliver the message to the RG service, which now will go the happy path scenario. Will perform the RG limit update and sec and publish a reply back to the broker, which will be picked up by our payment service. And the payment service, acting as the orchestrator, will decide on the next step in our Saga. This one is to command our wallet to perform the deposit, and that's what it does. It sends a command message to the broker, delivering it to the wallet service, deposit amount successfully, so the reply is sent back to our broker and read by our payment service. Now, here we have essentially what we have done is cut some corners. We have an orchestrator that also acts as a participant. We did this to gain some hopes, and I'm pretty sure at some point we will pay for it very expensively, but for now we're just keeping the flow a bit shorter. Once this is done, we will have the orchestrator order the communication service to notify the user, and then we're done. What's clear, all dotted arrows we have here essentially are message consumptions from the broker, right? So they can happen at any time. Now, 9 times out of 10, 99 times out of 100 probably, this flow will run instantaneously within within milliseconds. There will be this one time where we'll have increased load, we'll have network partitioning, some of our services will be down for maintenance, when this saga will take much, much longer to complete. And this is something we need to be upfront with our business owners. An overview of the orchestrated saga approach would be the following. We have this way that the orchestrator asks each participating party to perform what it is to perform. So this is the command reply pattern. Also, these are long-running transactions. They're called sagas for a reason, because it can take a while to complete. Other than that, most of the traits are pretty common with what we saw in the synchronous counterpart. It allows services to be much more granular and less coupled. It also makes our orchestrator be much more maintainable, and exactly because all code base is within the orchestrator. However, again, let's keep an eye not making the orchestrator too smart. It's a state machine that needs to be able to recover, and if you get an advice from our experiences with this approach, if you already don't have event-driven going on, or a message broker in your architecture, and you want to investigate how sagas would work for you, don't be like us. Don't go event-driven, for instance, and redesign your redesign. Use the orchestrated approach to test the waters, see how you feel about them, how you can support such a setup, and then you can implement other flows or redesign this one as you get more comfortable with the setup. In the introduction, in the agenda, I said that timeout and retry policies are the best way to achieve resilience and stability, when I should definitely have said they're also the most overlooked. A relatively recent study on timeout-related errors on big cloud platforms like Zookeeper, for example, had the specific finding that 31% of these errors were actually caused by missing timeout, no timeout configured at all, while 47% was because it was misconfigured. So essentially what this says, that these big natively distributed platforms, 8 times out of 10 got their timeout configuration wrong. So chances are that the average enterprise application, this percentage is at least the same, probably even much higher. So essentially, when we talk of timeouts, more or less 2 timeouts that come to mind. It's the connection timeout. What is the maximum amount of time that we allow ourselves to establish a TCP connection with the other party? And the read timeout. What is the maximum amount of time we allow for that conversation to conclude before we forcibly shut the connection down? The question that arises is why? Why do it? Why stop something in between within delivery? And the answer here is that we're saving on resources. Now, for every thread that we have waiting to get a response from the other party, we have a thread that cannot satisfy other incoming requests. Now, in the initial redesign of the betting flow that we saw earlier, where we had these chained requests, when we went live within the first couple of months, we would have the RG service, the last node in this flow, to just cough, and the whole thing would go down, exactly because we didn't have any timeout configured, and the cascading failures were pretty big. This is also demonstrable here. Now, what we see here is we have a downstream service that is misbehave, and we have 2 services that are connecting to this one. The red service does not have any timeout configured, while the green one does. Now, what we can see here is As time goes, more and more threads are occupied in the red service and they're not freed. So what the red service reaches is a thread starvation zone. Essentially, they don't have any more threads to satisfy other incoming requests. The green service, on the other hand, well, obviously it has its load increased because the requests that until they're timed out, they take some time, but this timeout kicking in gives us this buffer here, which gives us significant resources to handle other incoming requests. It's also interesting to have a look at how, from an error-generated point of view, how timeout versus no timeout appears. Now, again, we have a downstream service that starts to misbehave around here and recovers, let's say, around there. Two versions of the service. The blue one doesn't have any timeout configured. The blue one has timeout configured. The red one doesn't. So, two things interesting to notice is the blue one actually starts generating errors much earlier than the red one, and the red one starts throwing errors around here. This is because these are actual timeout errors. These are unavailability errors. So essentially, our service has gone dead now, and now this is why the errors escalate that highly, that quickly. And exactly because of that, it's the second point that around here, when the downstream service recovers, it's the blue one that stops having errors, while the red one keeps having errors, exactly because in this case, all the threads are hung, so some sort of manual intervention was required to recover. So how do you calculate the proper timeout value? It wouldn't be software engineering if there was a silver bullet, so there is none. But what I can share is some approaches that we've been using that can prove helpful, at least give you a rule of thumb on how to calculate the timeout. Now, given a downstream service that we're going to be connecting to, what we do is start calling it and measure the response times. We use these response times and we plot a histogram, and then we calculate the 99th percentile. Now, for critical services like the betting service that we saw earlier, this exactly will be the value that we'll be using as a read timeout. What this means is 99% of the requests will be successful, the 1% will be rejected. Now, depending on the service's criticality, depending on your own aggressiveness, on your organization's tolerance to risk and errors, you can go more aggressive than this, move to the 95th percentile, for example, or be more lenient, go to the 99.9, or add some sort of buffer. Whatever you do, you need to make sure that you figure out the tail latencies. Tail latencies is whatever is beyond that threshold that we've set, the 99th percentile. And why is it important to know the root causes? 3 reasons. First of all, these can be caused by simple network hiccups. This is the best case scenario, network hiccups, which is fair game. We're in a distributed system. We will definitely expecting some sort of delays. However, what we might have here could be some implementation quirk, some bug, some edge case that we haven't really considered. And usually it takes simple, small changes in the way our application is used, sometimes by the users themselves. We're not even involved. And these can get much higher percentage of requests and have a significant increase in your total response times. There's another reason why you should look into it, which we found out the hard way. In the initial version of our monolithic wallet, I mentioned that it was the wallet that was performing the responsible gaming checks. Now, the way it did was by retrieving transactions from the database to calculate what the user had already played. So what we found out was the users that were playing the most had the most transactions. So the users that were playing the most had the biggest delays in their bets, which is counterintuitive to business. So it's definitely, there's some hidden gems that you might find here. A timeout's best friend is the retry, and the typical example to demonstrate this is we have a wallet with a balance of 200 euros, and our user just asked to have a deposit of 500. Now, our wallet takes a little more time to respond, but it's successful and returns. However, the payment services timeout has kicked in, so it's no longer listening to the response. So what does it do? It retries. And again, we have a balance that was 700 because the first deposit was successful as far as wallet was concerned. And we've just added another 500 euro to the balance accounts, 500 euros worth of free bets. You might, I might find funny. My boss definitely didn't. So this is where it makes sense to keep in mind of idempotency, which is a way to make sure that retries are not also reprocessed. Generally, there are two schools of thought going in terms of idempotency. One is called request fingerprinting. Now, the concept is that this one involves only the server side, so the client side is unaware of what's going on. Now, what we can do is take the payload of a request that comes in, and then once we serve it, calculate some sort of hash function on it and store this result. Now, for every other incoming request, we have its hash function calculated and compare it with what we have already served. So now we know whether we have seen this payload before or not and handle it appropriately. Of course, there will be some cases where this won't make much sense if we have recurring payments, or if we think the cases of casino games where essentially we have the same payload over and over again. So in these cases, it makes sense to be a bit more deliberate when it comes to your idempotency. And you need to involve the client as well. So this is where client request IDs come in handy. Essentially, usually in the form of a header, what we do is have the client add an identifier. This identifier is different for every request, but it's the same for every request's retries. So this is a way that we can know on the server side whether we have seen it or not by simply storing this identifier. Now, of course, this also will have some edge cases. What do we do if we have the same identifying key but different payload, for example? But at least, again, you have a rule of thumb of knowing whether you have seen this request or not. There's a lot of things that you can follow up with in terms of stability and resilience in your system, adding some sort of exponential backoff in your retries, and then making sure that you add some jitter to it as well. Circuit breaking to make sure that the downstream service doesn't its downtime is handled correctly. Rate limiting to make sure that you rate your clients in the request they send you. So, closing. There's no such thing as a static or perfect architecture. Obviously, it evolves just like our business does. And before making any sort of architectural leap, like moving from a monolith to microservices, make sure that you have the proper buy-in. And it won't be only technical, and it won't be also only business-wise. You need to make sure that organizationally and operationally, you're able to handle this leap. And the main reason behind it is because you're moving into a really complex world, and especially in terms of distributed transactions, even more so if you want to achieve maximum availability. Finally, Baz Luhrmann said, don't forget your sunscreen. I say, don't forget your timeout. So that's all from me. I would like to thank the organizers for giving me the chance to share my experiences with you and you for joining today. Thank you very much.